So we are back to finish talking about electric generators and Faraday's law of induction. Screen. Sure, why not? Thank you. So let's get into this. We're going to have a woo clap question right here off the bat. Is what?
That kind of problem.
It's a potential. Okay, so here is our first question. What had to occur for an EMF to form in a wire within a constant magnetic field? So this is just referring back to what we talked about in class on Friday. Woohoo, first answer. Okay, all 9 of the people who are participating have answered. So the answers we got were 0, 3, 5, 1, 0, 0, 0. So recalling what we had a magnetic field and then we had a wire or rod, and that rod was like that with a velocity like that. So the velocity has to be perpendicular to the magnetic field. Hooray. So, of course, parallel would be wrong. If the wire was stationary, no go, because you don't have the magnetic force on the charges. Moving parallel to it, no go. You don't have the force in the charges. Magnetized wasn't an issue for the wire. Net negative, positive, or zero charge, nope, those were unrelated. So that's what we needed with what we studied in class on Friday up until the last 5 minutes. So I tried to really quickly jump ahead just so I could introduce Faraday's law of induction. So in 1831, Michael Faraday, go forward. 1831, Michael Faraday determined there were 2 ways actually to induce a charge. One was having a conductor moving, as we just saw, and the other one was to have a changing magnetic field going through a loop. And so that's the Faraday's law, is having a changing magnetic field going through a loop. And so it has to do with flux. Here we have a loop, and remember I said the flux is BA times cosine of the angle between the magnetic field and the area. Remember, the direction for the area is the normal to the loop. So this loop being in the plane of the screen, the area is into or out of the screen. So cosine theta is either 0 or 180 degrees. And so we'll just go with the magnitude, say it's 1. So in this top one, we have 1, 2, 3, 4, 5, 6 x's going through. So we could say the flux is 6 something. The bottom one, we have 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12 x's going through. That's twice the number of x's, so twice the flux. And Faraday said if we go from one state to the other, that's going to induce a current in the loop. And so it's a second way that we can induce a current or induce a voltage, depending on which way you look at it. If you have a loop you're not really going to have a voltage induced because it's just going to make the charge move in the loop. Right? You'd have to have a resistance to have a voltage drop. But it's going to make that current go in a loop. And so then we have the calculation of the magnetic flux. This I've already talked about more than necessary. This is an important thing, though, to keep in mind. You have the area, you have the angle. If the angle was 0 degrees here, you would actually have more x's going through that surface than if it's at, well, 90 degrees. How many lines would be going through the surface? 0. Right? So as you tip between the number of lines going through the surface changes, which is why the flux depends on that angle. And of course, I thought it was important to point out that the units were Webers for magnetic flux. So we ended with this, I think we ended with this slide. We might have gone a little bit quicker. What was the difference between this equation and this equation? Okay, the second one accounts for coils, the first one doesn't. If you want to write it out, you can just write it like that, and then it's the same both ways. Change in VA cosine theta over change in time, and N being the number of coils that you're doing this for. So if you have a change, well, what three things could change to induce a voltage? Remember that script E means voltage, EMF. What three things could change to induce a voltage? Area is one. Magnetic field. And the last one? Someone? What's the last thing, Isabel, that could change to induce a voltage? We already have magnetic field and area. What's the last thing that could change and would cause us to have an induced voltage? Not the velocity. The last thing is the angle here, theta. So if you have a change in the magnetic field, it'll induce a voltage. If you have a change in the area of your loops, it'll induce a voltage. Or if you have a change in the angle between your magnetic field and the area, it will induce a voltage. Any one of those will. So, question number 2, what will not produce a magnetic field? A magnetic field? This should have been electric.
Are there root clap questions in your slides?
These are the Woo Clap questions. I have Woo Clap separate, but I put the questions here in the slide, yes.
So yes.
And yeah, like I said, it should have been electric field / voltage. I can't believe I made that typo. All right, we have all people participating now. That's good. 6 answers so far. It's going to time out here. I restarted it so the 4 that didn't answer still can answer. 3 remaining. 2, 1. Last one. There we go. Everybody's answered. Thank you. 811. Well, the preponderance, the large majority, said that a change in magnetic flux through a stationary coil will not produce an electric field or a voltage. Correct answer was this. If the coil is moving in a constant magnetic field, that goes back to the picture we had before where we had a loop, and then we had magnetic field here. We had the loop moving into it. And when it was moving in, there was an induced EMF. But when it was in, you had the electric fields pushing against each other actually would make, I should be clear, maybe I can give you justification for your answer. If it's in the middle of here moving, you would have an electric field like this. You'd have no current flowing. So I really should have said will produce change all of that. I should have said a current. Because, yeah, the question was bad. So I'll give it to you, no matter what you answered. So how do we make a generator? What does this look like to you? We have a north magnet, a south magnet with a loop in it. An alternator. Alternator is a different design. I'll talk about that a little. That's what the picture for electric motor that we studied last week looks like. Electric motors and electric generators have fundamentally the same design. They both have a rotating loop in an external magnetic field. So what's the difference in an electric generator and an electric motor? One of them uses electricity to make mechanical motion. One of them uses mechanical motion to generate electricity. They're just the reverse of each other. So with this, if I force current through the wires, it turns it into a motor. If I force that loop to turn, then it's going to make it into a generator. Now, in the peruse all questions, people were talking about what is a back EMF. Well, since an electric motor and electric generator are the same design, when you put current through the motor, it starts to rotate. But as soon as it starts to rotate, it starts to generate electricity. And that electricity it generates, we call the back EMF, the voltage that's being produced by the motor because we have a coil rotating the electric field. Now, how is this going to generate electricity? We saw that the EMF is equal to minus N change in BA cosine theta over change in T. Stop that finger. The magnetic field is not changing. The area is not changing, but the angle is changing. So if I write theta is equal to omega t, that is a constant rate of rotation, then this is equal to minus NBA delta cosine of omega t over delta t. Now, only one of you here has to know calculus. This here is truly a derivative. If you take that derivative of cosine is biggest sine. So that's going to be negative omega. Oh, come on, fingers. My fingers hit wrong places. I have that set. It just doesn't work perfectly. Or in other words, notice I have a minus and minus, so that's omega NBA sine of omega t. Hey, there I wasn't even touching it. It still did it. Omega t. So the EMF, the electromotive force, the voltage, generated by this generator is omega. What is omega? It's the angular velocity. It's the rate at which it's rotating, measured in radians per second, multiplied by n, the number of loops, multiplied by b, the magnitude of the magnetic field, multiplied by a, the area of that loop, and then times sine of omega t. So when omega t is 0, we have 0 voltage. When omega t is 90 degrees, we have omega NBA. When omega t is minus 90 degrees, we have minus omega NBA. Buddy.
Do you think there'll ever be a time when one of the equations is we derived that from the variable equation? So do you think there'll ever be a time when one of the other equations will be more helpful, or should we just focus on this one?
When you say one of the other,
Like,
you mean the
one
process of getting there?
no, like one of the other forms of the same, because it's technically the same equation, just in different.
Yeah, there are times when this is going to be most useful,
Right.
and there are other times. Come on, one more. Maybe one more. Go backward, please. There are other times when this is going to be more useful.
So, okay, so are there like, should we focus on those two or just like be aware of all of them?
Well, you're going to have all of them on your equation sheet. And depending on the situation, you want to use a different thing. If it's a generator, you want to use the one we just derived. But if it's not a generator, well, then that's not going to work for you.
So this equation only works for the generator or for the generator and the motor?
Well, we were only talking about the generator aspect. Remember, a motor and a generator are the same design fundamentally. Now, a motor is generally optimized for one purpose and generator optimized for the other. So they're not optimized to work equally. But they will both do the same thing. In fact, my understanding is in early automobiles, they had a generator and you started it with a hand crank. And then some genius said, hey, wait a minute, we got a generator, that's an electric motor. And so the generator and electric motor were both used. You would use a battery and put current through the generator and connect it to the engine to start the engine. And then after that, you use it to charge the battery as a generator. These days, we use an alternator, what Andy had mentioned. The difference in an alternator and a generator is what's moving. An alternator has a loop with a whole bunch of little coils on it. A whole bunch of coils out here on the loop. And then it has a rotating magnet inside. So the magnet is rotating and the loops are stationary. That's good for a couple of reasons. One reason is the loops are much more fragile than the magnet. So having the fragile part stationary gives it added longevity.
Are we talking about motors or generators right now?
Neither. Alternator.
Okay.
So the alternator is just a different design. It's still generating electricity. But now you have all these loops on the outside. And for the magnet is actually, you have, let's say this hand is north and this hand is south, so there's a bar between. So you have the north and the south, and they interleave them. And so you have north-south passes very quickly as it rotates. Because what makes the voltage? It's the rate at which the magnetic field is changing. So if you change from north to south quicker, right, you have just a small rotation, you change from north to south, you'll have a larger voltage produced. So the alternator is very much optimized for generating electricity, and it won't work as a motor because it's not designed like a motor. So you can't start your car with an alternator. Hence, you have a starter motor and separately an alternator in today's cars. So the starter motor looks like this generator here. Not going to go through the picture here. Instead, we've already worked this out, the EMF produced by the generator. And so let's do a problem. And I think this is simple enough that you can do it right off the bat. But if you have questions, don't hesitate. Say, ooh, I'm not sure. Steer me straight. I want to create a generator that produces a peak voltage of 170 volts at frequency of 60 hertz using magnetic field 30 millitesla. My coils have an area of 15 centimeters squared.
So we're looking for N.
We're looking for N. Now, probably a lot of you have this written down, but in case you don't, can somebody quote for me what the equation is we need to use?
E equals WNVA sine WT.
So I'm going to drop off the sine omega t because we're looking for the peak. And remember that is omega, not W.
So what does omega stand for again?
Okay, so what does omega stand for? Somebody want to straighten that out? Which is 2 pi times the frequency. Which is what I expect people to ask me. It's 0.15 centimeters squared times 1 meter of 1 centimeter squared. It's the 1.5 meters squared.
You could just take the No, it's fine. I find it. You're welcome.
Oh, wait. I'm gonna have a different version.
Yeah,
So
and
it's
you
just
just
two meters. Yeah.
So like the E is up ET, so you can
Yes.
So I'm just gonna put 170 equals that.
Yeah, so 170 equals that such, and we're solving for n.
That sounds reasonable.
Okay, so you plug it. You're right. You guys see a calculator?
No, I've got ones that are mine here, but that's all. Oh, yeah, how-
131,400.
Uh-oh. What'd you get? Okay, 10,000 maybe? She got 10,000.
I got 31,000.
We've got some variations here. Most people have numbers.
Look at my calculator. Okay. What is this units of? I didn't take it.
What was that?
What are the units of N?
The units of n is turns. It's unitless.
It's not like meters or something.
No,
like
no.
Okay, never mind, I got 10,000.
Okay, solving for n, just EMF over omega BA. So that's going to be 170 volts divided by my omega, which is 2 pi times 60 hertz, times my magnetic field, which is 0.030 Teslas, times my area, which is 15.0 centimeters squared. Come on.
Oh, and Joe, also your units wrong, because we were given 30 milliteslas, and we need to convert that to
So it'd be like
teslas.
1/10
And
of
same with 15
What's
centimeters
squared
we
though? Is the
can
one
make
over?
that.
The 1 over 100 is what's squared. Because we need to cancel both of the centimeters and centimeters squared. So, is this what you did?
I got
What was
10,020.
the answer? The 10,000? I got 10,045. 20 instead of, I got 10,020. Around here. I just got 165.
No,
Oh.
negative.
Centimeters.
Right, because we're squaring them.
Yeah.
So if it's.
So it's really, so it's 15 minutes. Right.
So it's just like
So basically it's 15,500.
Divided by 60.
Yeah, I got that.
Yep. So the answer I got is 10 to correct sig figs, just 10,000. And there's no units there. It's unitless. So, what was the most difficult thing about that calculation? Converting units. Remembering how to convert units. Just like the problem that people were asking about before class, the most difficult part is adding vectors. Things that we've done for a long time, but we tend to forget if it hasn't been done recently. Now, yeah, no, that's good. It's after this slide that I want to do especially. So, this is what the voltage output is going to look like. It's going between omega NBA, which we said was 170 volts, to minus omega NBA, minus 170 volts. And it has a frequency of 60 hertz. We call this an AC signal, alternating current signal. For lab tomorrow, we're going to do all of the electric AC circuits we're going to do in this class. We're going to do lab tomorrow. But we're going to be dealing with AC, alternating current. What is the average voltage here? That's the blue line. What's the average? 0. So V average is 0. Well, that makes things a little annoying. For AC voltage, your average is 0. So we don't go ahead and talk about our AC voltage as being 0 volts. Because it doesn't matter what the peak voltage is, you always get the same value. Now, we also don't generally identify it by the peak voltage, which it seems like peak voltage makes sense. But we go with the RMS voltage instead. The reason we use the RMS voltage is because our power equations and everything stay the same. So how do you find RMS? Okay, RMS is root mean squared. So the first thing you do is the last thing in RMS. The first thing you do is square it. So if I square this wave, actually, if I square it, does anybody know what it looks like offhand? It's another sine wave, but now it goes from 0 to a peak of 170 volts quantity squared. Notice the frequency has doubled when I squared it. What's the average of this sine wave? What is it? Yes. Now I'm just going to put V max. Come on. V max squared over 2, so it's generic. So the first thing I did was I squared it. That's why I showed it the graph. Then I did the mean. That's finding the average of the V squared. What's the last step to find the RMS value? Not quite rhetorical, but close enough. I have to take the root, in this case, the square root. So VRMS is equal to the square root of Vmax squared over 2. Well, what's the square root of Vmax squared? Vmax, right. So that's equal to Vmax divided by the square root of 2. So the RMS voltage, which is what we actually use to designate the output voltage coming out of the wires here, is the peak voltage divided by square root of 2. So, second problem for you. What was the RMS voltage of our 170 volt generator? It had a peak voltage of 170 volts. What's the RMS voltage? Okay, I'm just going to go with what he said.
Oh yeah, I was right. Holy cow, I was totally guessing.
Yeah, that's 1.2.
So the voltage we have coming out of here is 120 volts. That's the RMS value. So it means it has a peak voltage of 170 volts. What's its minimum voltage?
Less than 100 volt.
How old is it? I have no idea how old. What are you asking? Is it zero?
It's negative 170. The peak is 170. The minimum is minus 170. Yeah, we're just using a symmetric sine wave, so the average is 0. The R.
So like, would it ever be, because we did have that, but would it be the baseline, the middle line ever not be 0?
You can bias something because remember, voltages are always referenced to something. Usually we reference to the earth, but you could reference to something else. Yes.
But like in this class, should we just say it's probably going to be at 0?
Yeah, unless you are told otherwise.
Okay.
Okay, so we've got the RMS voltage thing down. DC generator. What's the difference in DC and AC? AC is what we just finished. It was alternating current, or the voltage is going symmetrically above and below 0. Direct is not constant, but it's always the same sign. It never goes below 0. It's always positive, if you will, or always negative. So how can we take the output of our generator and make it DC? Because like if you want to charge a battery, if you have an AC generator connected to a battery, Half the time you're charging, half the time you're discharging it, all you're doing is tearing up your battery, right? So you want to rectify it, make it right, make it into a DC source. So there's a couple ways you can do it. One is the same thing as we use to make a DC motor. Remember the DC motor, we had the split armature with the brushes so you could change which one's positive, which one's negative as it goes around. Well, you can do that on your generator as well. And so you can make a rectified signal now. So this we'd say is rectified. You see I highlighted it in red. That still wouldn't be the best for your car battery. So there's other things that we might do to make this a better signal for our car. For one, we might take the generator. So here's going to be my generator. That there because it's putting out an AC. We go through something to rectify it. That something to rectify it is usually a diode bridge. And I will actually talk about this in just a moment after I get it drawn. Anybody know what a diode is? Actually, the word does come from two.
Yeah.
A diode is made, the original word actually comes from vacuum tubes. But the diode has two sides, a positive side and a negative side. And you make it with a semiconductor these days. And what the diode is, so that's the symbol for a diode. And it's a one-way gate. It will allow current to flow the direction of the arrow, but not the other direction. And so with this design that's called the diode bridge, you're always going to have this side is positive and this side is negative. And so then that makes it rectified if I use my outputs there. And so next thing I'm going to do is I want to stabilize it. And so I put something that stores energy in the form of an electric field in between those two. That's going to store energy so you charge it up. It's never discharging, right? It's always charging. And so what that's going to do is make your voltage so it actually looks something like this. Okay, not that upward spike, but so it's much closer to a constant voltage because you store energy in the capacitor and then the capacitor gives you energy when the voltages are lower. Question, Claudia, just Bauermeister.
Thank you. Two questions. So, first one, what does the T stand for in equation?
Time.
So then, is the time that says like, is that like E function of time? Equals?
Yes.
So is that time the same as the time that you plug into the equation?
Right. You put time in the right-hand side to use the voltage at that time. So the E parenthesis, well, epsilon parenthesis T means the voltage at time T.
Okay.
Is that a question? Or were those?
Those were the two
Okay.
questions. Yeah.
So just to reiterate, what is the point of this funny green thing that we call the diode bridge? What's the point of this diode bridge here? To make it DC instead of AC, to rectify it.
So that's what a diode does?
Well, that's what a diode bridge does. A diode is a one-way gate.
Yeah.
So if I have a circuit like this, there is something seriously wrong right now. If I have a circuit like this, current just flows like normal because that diode allows current to flow in the direction of the arrow. So I'm going to have current go like this, no problem. But if I reverse that diode, if I make my circuit like this, then there's no current because it will stop current from going against the arrow of the diode.
So it's the bridge, you said?
Well, so the bridge is made out of 4 of those diodes. and the diodes are arranged, so it will only allow current to flow to make one side positive and one side negative.
So, sorry,
Go ahead.
in that picture, the diode is like that triangle.
Well, it's a diamond shape. Well, okay, diode is this here. Sorry. Yes. The whole thing with it has the line at the end and the arrow both.
That makes sense.
Okay. This is describing how more sophisticated systems work, like the brushes. Let's just move over that. Which parts are necessary for an AC generator? There are two answers. So not a DC one, but an AC one.
And this is different from what you said before the alternator.
Right, this is not alternator, it's an AC generator.
What is AC stand for?
Alternating current,
Alternator. And then DC is the
direct current.
director. Yeah.
What section are diodes in?
I think they're in the future section. I think they're coming
So
up.
it's not something that we know right now.
Right, they come up when we get to modern physics and talking about band structures.
What section are we in right now that we're working in?
I think it's either 23 or 24. Not sure. Okay, everyone's answered. Our answers we got were 7, 4, 0, 5, 3. Okay, split commutator. What's the point of a split commutator? To make it DC. So clearly that's not necessary to make it AC. Strong magnetic field? Absolutely. Remember, E is equal to omega NBA sine of omega T. So that magnetic field, boom. Electric field? There ain't no electric field in that. Magnetic wires? No. You need the rotating coil, the omega. N is the number of turns in the coil. I can see how you would say that's N. You could also say that's
omega
A.
was the frequency, 2 pi times the frequency.
Yeah.
How does that work? As it goes
So
in?
the omega is telling you how rapidly it's rotating.
Oh.
So yeah, I mean, what I point to for that one is a little bit confusing, but I point to the omega because it's the number that directly has to do with rotation. Okay, any questions about that?
See you later.
See you later. Well, I will be here all week long.
Our test isn't this week or next week. The week after that.
Next.
It's next week.
It's next week.
Yeah.
Cool. Okay.
Right, because we postponed the other test by a week.
Next week.
All right. That's actually the end of what I had prepared, but let's talk about a few things to make sure that we're not confused. Today we talked.
I am very sure that I am.
Okay, so that's why we should talk about these. Today we talked about generators. What is the basic principle on which the generator operates? Physics isn't a basic principle. It operates on Faraday's law of induction, that we induce a voltage when we have a changing magnetic flux. So the generator was an example of Faraday's law of Faraday's law of induction. Other examples then, anytime that you have a coil if you put a current through the coil, we learned that that creates a magnetic field, right? If you have a changing current, that means the magnetic field is also going to change. But if you have a changing current, that means you have a changing magnetic flux. And so if you have a coil with a current going through it, it's going to induce a voltage. We call this an inductor. And I am going to go to the whiteboard option here. Maybe. Told you to go to the whiteboard. Okay. Maybe I have to go back to get to the whiteboard. Oops. Oh, I did not mean to do that. That just deleted all of my writing.
Control Z, Control Z.
I hit Control Z. I hit the wrong button in my haste. Well, I am really sorry I erased all my comments. All I wanted to do was to go here. Okay, so this here in an electric circuit is how we draw a coil. And we call this an inductor. If you have current going through the inductor, it's going to make a magnetic field. And I did not tell it to stop. You have a magnetic field that's equal to mu watt times N over L, or actually I have to use a script L, times.
It has a mind of its own.
It does. Okay, I'm going to go to I'm just going to use the board.
I do need to keep
Okay, I will keep that on the board and work around it. So, third time. So the magnetic field is produced inside of that coil. Mu watt times capital N over L. Capital N is the number of turns. Lowercase l is the physical length. Multiplied by the current. Mu watt is what we have if it's an air core, if there's nothing inside of that coil. Something I haven't talked about heretofore, I was going to do a demonstration, is, I'll just do the demonstration in the lab. If you put something like iron in there, iron is a magnetic material. It has a mu that is much higher than the permeability of free space. And so if you use something that's not air, you change that from mu aught to mu. And it will make it have a much bigger magnetic field if you put iron in there. And so oftentimes your inductors have an iron core to get a much bigger magnetic field. Now you have that magnetic field, and so that means that you have a magnetic flux. And I'm going to put the N out here just. So N times the flux is equal to N times the magnetic field times the area. Putting in that magnetic field, yeah, I got things out of order, but it's correct. So that's what you have for the magnetic flux. But now consider what if I is I0 cosine of omega t if you have an alternating current going through there. If you have an alternating current, what's going to be happening to the magnetic field? It's going to be changing. It goes up, then it goes down, then it goes up, then it goes down. So the magnetic field is constantly changing. But Faraday's law of induction says induced EMF is equal to, oops, Let's just put flux in there instead of all that. So that's the induced EMF. It's going to induce EMF if the magnetic flux is changing because the magnetic field is changing. So it turns out that that's going to be equal to minus mu n squared I0 omega. Actually, minus 2 omega plus.
So what we're doing right now is we're taking an inductor coil and considering what happens if we apply an alternating current to it.
Yes.
Because we have an alternating current, we have a changing magnetic field, which causes a magnetic flux. Or a changing magnetic
flux, which then induces a voltage.
And that, okay. So it's
And so this voltage here, this induced EMF, is the back EMF again for now, instead of a motor, for the inductor. And so this here is going to be considered with a plus and a minus sign with a voltage. Now this is an alternating voltage, right? But notice the current was cosine and this is sine because we had to take the change in. So it's out of phase by 90 degrees. That is when the current is maximum, the voltage is going to be 0. When the current is 0, the voltage is going to be maximum. And so in lab tomorrow, we're going to be looking at that relationship. And the inductor, we actually simplify this equation quite a bit by just saying L is the inductance and giving it a value, which we'll talk about in lab tomorrow. Yes?
So then is the voltage like causing the current or is the voltage causing a lag in the current?
Well, in this case, we're driving it with the current, which creates the magnetic field, which then creates the back EMF.
Okay.
Now, one last thing that's important for us before I stop, I have 1 minute left, is Lenz's law. Faraday's law of induction says that a changing magnetic flux induces a voltage. Lenz's law tells us what direction the current will flow. L-E-N-Z apostrophe S because it's possessive.
And that's just the negative in the same law that we already learned.
Well, the negative is basically to point you to Lenz's law.
Okay.
Yes, it does mathematically work out that way.
Okay.
But to me, it's just to point to Lenz's law. Because if I have a coil here and the magnetic field gets bigger going down, Lenz's law says it's going to induce a current to oppose the change. So since the change was downward, it's going to make a magnetic field that's upward, which means the current's going to go that direction according to the right-hand rule.
Okay.
If the magnetic field is down and getting weaker, what direction is the change?
Down and getting weaker. So
Down and weaker means the change is up. So then it's going to have opposite. Okay, the first case should have been like this. The second case is like this. So magnetic field being down in both cases, we have opposite direction if one's getting stronger versus weaker. So you always have to look at that. Lenz's law is telling you which direction the current's going to go. All right, we are done for the day. I'll see you for lab mañana. We will be doing AC circuits. Oh, I can't believe I erased everything. Oh, yeah, and I have that on the recording.